Welcome back to Multigrid Methods. Today we're continuing our discussion about this method of subspace corrections. And we want to get into rather deeply into this method of successive subspace optimization methods. I want to talk about the convergence of that method. And then I want to start to think about abstracting that method, generalizing that method a little bit more so that we can give ourselves a little more flexibility in how we solve problems. I also want to relate this back to our multigrid methods that we've been discussing way back in previous chapters. Try to connect it to what we've already done with our finite element based multigrid methods. Although this can be also done in the context of cell-centered finite differences as well. But that's the basic roadmap. We want to connect this mostly, and it's most easily done, to the finite element method. So I've added another section to this one. The current slides are a little bit different than they were previously. I want to show you kind of exactly what is new with what we're working with here. Um, Besides that, so I changed a few slides in these sections and I added this section. But in any case, this is part one of two. There'll be two more sections coming, and that's where we really talk about how to do this generalization process. All right, so the goal is, of course, to solve some sort of optimization problem, but I would say that's not really our goal. The the point is oftentimes we're given a partial differential equation that we have to solve, and from that we go backwards and think about, well, what is the optimization problem that's associated with that? If you're studying physics or an engineering problem, oftentimes you work in this way. One implies two. So we start with the physical energy problem, and then we derive our Euler-Lagrange equation 2, and then we try to solve 2. In other cases, we're going from 2 and trying to get back to 1. We're given a PDE, and somebody says, well, does that have an energy? Does it have some sort of structure, deeper structure associated to it, which you could leverage? But in any case, we're trying to solve this optimization problem, which is entirely equivalent to solving this Euler-Lagrange equation, this Euler-Lagrange problem. And if you're taking currently this course in calculus of variations is running at the University of Tennessee here, then there's a lot of overlap in what's going on. So I changed the assumptions around a little bit with the energy. We've had three assumptions previously. I wanted to condense that down to just two different assumptions. And to be quite honest with you, this may change a little bit further as things go along and I refine how this is working in the book. But basically, we've got assumptions that we have about the energy. What assumptions make this have a unique solution? Well, if we assume that E is Frechet differentiable and strongly convex with a constant mu, then we know that this problem has a unique global minimum. And we also know that it satisfies the Euler-Lagrange equation, or just the Euler equation. So we're going to bundle those two things up and call that assumption E0. The next assumption is needed for all practical points, and that is the assumption that E is locally Lipschitz smooth on V. And so what I'm going to call E1 is then essentially E0 plus that additional point. And you need that in order to prove that our standard algorithms converge. For example, we introduced a couple of classes ago this gradient descent method, and we analyzed it and showed that it converges under the assumption that E1 holds. So E1 is E0, in other words, Frechet differentiable plus the strong convexity condition, in addition to well, that's E0 is those two, and E1 is that in addition to E being locally Lipschitz smooth. Now, when I say that it's locally Lipschitz smooth, that means that the derivative is locally Lipschitz continuous, and that means that there's a Lipschitz constant associated for every bounded set that you encounter. And so the the typical thing that we will do is, unless it's expressed otherwise, if we're on some bounded set B, then we're going to say that the Lipschitz smoothness constant associated that set is going to be just L sub B. Okay, and I think I mentioned that last time. All right, so as we saw in the last chapter, the gradient descent method will converge, but it's too slow for convergence to be practical, and so we want to come up with something a little bit different. Now, subspace decomposition, we described this last time, and this is the same as before. I just decided to split this definition into 2 or 3 parts. So now I've got the core definition about subspace decomposition is separated by itself. So we say a collection of subspaces is called a subspace decomposition if and only if each one of these VIs is norm closed subspace of V. It doesn't have to be finite dimensional, but usually it is for all of our practical computations. And V is equal to the sum of V1 plus V2 up to Vn. So that means that every generic V, if I have a generic V in V, then this can be written as, or I should say there exists a bunch of little VIs such that V is equal to the sum of the VIs. Okay, that's what that means, basically. I can always find a decomposition in this way. All right, I meant to put an example in here, but didn't get round to it, so it's blank. Okay, so there's your example. So I added in chapter 10, for those of you who are locals, I guess it's chapter 10. Those of you who don't have the book, it's chapter it's chapter 9. But in any case, those of you who have a copy of the book, chapter 10 has a nice little example in there which goes there. It's new, and basically it relates how, remember in that chapter we talked about these prolongation matrices, and we described subspace decomposition in terms of these prolongation matrices. Well, in an example that I added there in chapter 10, I basically relate that description of a subspace decomposition to our new subspace, or our new notion of subspace decomposition. And so for that reason, it's quite useful for you to go have a look at it and see what it's saying there. So if you have some time, go back and look at that example. It's a new example back in chapter 10, which relates this idea of subspace decomposition with the idea of subspace decomposition based on prolongation matrices. Okay. Now, we went over this last time. We said that a subspace decomposition is stable if and only if if and only if there exists a constant such that there exists a decomposition that is always stable in that norm sense. Okay, so I'm always guaranteed that I can find VIs such that this stability condition holds. So what does this look like? In the finite element context, we're going to revisit this when we visit the next chapter. And so I'm not going to give you an example of what this looks like here, although there are finite dimensional examples which don't rely on finite elements that I could have drawn up and given to you. We'll wait on that until we discuss the finite element implementation of these ideas in the next chapter. For now, let's just take this as a definition. Some decompositions are stable in this sense, and some subspace decompositions are not. And so we'll come back and revisit this momentarily. Okay, so there are always, for a stable decomposition, there has to exist a constant such that for every v, there exists decomposition vectors such that this stability statement holds. So you can imagine there could be a subspace decomposition where this doesn't quite work, okay? And so we want to talk about when that happens. But we're mostly interested in the case when of course it's stable and nice things happen. And we'll see where this gets used whenever we're proving theorems about the convergence of algorithms. And we also talked about this last time. I tried to explain this and pretty much failed. I mean, this strengthened Cauchy-Schwarz inequality condition is rather complicated and difficult to explain. And so basically I punted on this one and said, I can't really explain what it means, but you'll see where it's used, and we'll also explain how certain energies have this property when we look at the finite element implementation in the next chapter. So I'm going to do the same thing here. Basically, we'll come back to this. All right, so a couple of remarks. We've already gone through this, so I'm going to skip these remarks. And I want to get on to reminding you what we meant by a successive subspace optimization method. Right, so again, keep in mind what we're trying to do. Keep in mind what we're trying to do. We're trying to find a U, which is the argument that minimizes some energy over some energy space that is a Hilbert space. And we said if E is sufficiently smooth, that is, if it's Fauché differentiable, then this can be realized or rewritten as, or I should say it as, we can show that this problem is equivalent to solving a problem like this. This is the so-called Euler equation or Euler-Lagrange equation. And this is nothing more than, and I think we mentioned this last time, if an energy is convex and coercive, and so if we assume that it's strongly convex, and this is certainly the case, and is differentiable, then what we do is look for the place where the derivative is equal to 0, and that uniquely characterizes where the minimum is. So in higher, in infinite dimensional setting, we can't simply say, we'll just set the derivative equal to 0. That's essentially equivalent to saying or making a statement like this. Okay, so there's the derivative. And so this is essentially saying the derivative is equal to 0. By the way, if you're into functional analysis, the way we write this is as follows. We say that this is equal to 0 in the dual space. Okay, so it kind of is the same thing as something up here. So this might be f of u. And of course, we're looking for f prime of u equal to 0. In other words, this is written as dfu equals 0. Okay. So this would be the equivalent way of saying that in this infinite dimensional setting, these two objects are the same, or these two statements are the same. Now, this object here, denoted by these angle brackets, is what we call the dual pairing. So this object is a functional, and this object, of course, is from the Hilbert space. And so this means the pairing of the functional, linear functional, with the object from the Hilbert space. And it simply means you evaluate that functional at this point and set it equal to 0. This whole thing has to be equal is just a real number, and we're saying that real number is equal to 0 for all W that you throw in there. So this is the problem we're trying to solve, okay? And we're going to solve this by something called the successive subspace optimization method. So the idea is you have before you some subspace decomposition, VI, I equals 1 to n, and we're gonna assume everything about this that makes this problem doable or nice as we need it. So for example, right now we'll just assume that it's a subspace decomposition, but we're going to come back later and say that it's a stable decomposition and the strength in Cauchy-Schwarz inequality holds with respect for the energy with respect to this decomposition. But for now, we're just going to define this method. All right, so the successive subspace optimization method, what is it? Well, it's like most of the algorithms we deal with in this book, it's an iterative algorithm. You put in UK and you're going to get UK plus 1 out, and hopefully it's going to converge to the unique solution U that minimizes that energy. But here's the algorithm for computing this this from that. We're going to first set U0K equal, or sorry, V0K equal to UK. Okay, so that's just an initialization step. Then we're going to cycle through all the subspaces that we have. Remember, we have a subspace decomposition. There are n of those, so we're going to cycle through all n. And the first thing we do is we're going to define an energy section along this subspace VI, and we're going to base this energy section at the point VI minus 1K. So to start with, we're going to be doing I equals 1, and so VI minus 1 is going to be V0, so that's just the point that we just set. And so basically we're successively going through, and the picture of it is like this. We're trying to get here down to U, and we've got some energy which has its isosurf or isocontours. And so we're basically starting out here at let's say V0. Okay. Right? And the first thing is we figure out, well, what's the direction, the first direction we're going to look in. And so these aren't necessarily one-dimensional subspaces, but we're going to pretend they are. So if you pretend it's a one-dimensional subspace, then you create an energy section along that dimension, okay? So I can think about this as being a hyperplane, and the hyperplane is described by points like that. It's the points that are V0K plus W, where W is along V1 to start with. So we're going to minimize along that direction, okay? So that's called an energy section, and we're going to minimize that. When we minimize that, that's going to give us something called a correction. So you can think about this as a little bit like the coarse grid correction that we encountered in Multigrid. Once we have that that minimum, and it looks like if I'm in this one-dimensional setting here, it looks like the minimum is somewhere maybe there, right? Because I can think about cutting this ellipsoidal energy, cutting it along a section, a one-dimensional section, and then I'm going to minimize that along that one dimension. And so looks like the minimum point is going to be there. Okay, once I get that minimum, I'm going to call that the correction. Then I'm going to add that to my previous best guess, and that updates my best guess, and then I go on to the next subspace and I do it again. So my first update is going to get me to this point here, and that I'm going to call V1K. Okay, and then I look at my next subspace. I'm going to write that next subspace is going to be in red. It didn't work. Snap into place. There we go. So that's my next subspace. I'm going to look along that direction and minimize. And then it looks like if I minimize along that direction, I'm going to get maybe to there. And you can see I'm making, or I should be at least making progress towards U. All right. And then when I get to my last subspace and compute the subspace correction, that gets me VNK, and that's my final update. All right, so I have to run through all of these subspaces in order to just update this from UK to UK plus 1. So that's this thing called the successive subspace optimization approach. That's sort of the cornerstone for all the work that we do in this chapter. It turns out this algorithm is not so useful, however, and so we want to generalize that. And we'll see. I don't know how much we'll be able to get into that generalization. I'm going to talk about it a little bit, but the analysis of that is thick and complicated. So we might not be able to finish that with the few classes that we have left. I think, what, 3 classes left. So we'll do our best, but we've got to wrap this up at some point. All right, now I talked about this last time too. There's this concept called the fundamental orthogonality, and that just means that when we do this optimization here, we're actually solving, we can actually think about this as solving an Euler-Lagrange or an Euler equation, right? Because this energy section here that's defined by this is a differentiable, Frechet differentiable, strongly convex energy in and of itself, right, over a subspace. So when we solve that problem, really what we end up solving is a Euler equation of a form like this, where the W's here are in the subspace. Now, once we solve that problem, it has the solution EI, but notice that EIK added onto VI minus 1K, which is how JI is defined. JI is defined like that. Once I add this correction on here, that's EIK. This whole thing just becomes VI, so I can replace VI in there. So this is VI. So this is the orthogonality that I'm talking about. This equals to 0 for all W. That's the fundamental orthogonality relation. That says that once I've updated this point to VIK, then this object here is orthogonal to all the points W and VI. So what that looks like is basically here's VI. And my point is basically orthogonal to that, okay? Orthogonal to that subspace. All right, so that's the fundamental orthogonality of the solver. We talked about that last time. It turns out, so if the energy is, so this is sort of a classically known problem. So if my energy looks like this, E is equal to 1/2 X transpose A X minus X transpose F. And A is SPD. Okay, then this is equivalent to solving AX equals, minimizing this energy is equivalent to solving AX equals F. You probably encountered this in a numerical analysis course before. Now, if I want to do Gauss-Seidel on this, then it turns out Gauss-Seidel can be realized as the successive subspace optimization method where I choose Rn in a very specific way. I'm going to choose Rn to be equal to the space spanned by E1 hat plus the space spanned by E2 hat plus ... plus the space spanned by En hat. Okay, so you're just taking the various directions and you're decomposing Rn like this. Now, if I do this subspace decomposition or successive subspace optimization approach with this decomposition, then I get Gauss-Seidel. It's just the Gauss-Seidel method. So that means that successive subspace optimization is really a kind of generalization of Gauss-Seidel. Now, what happens if this energy is not quadratic. This is a quadratic energy, a positive quadratic energy, sort of built upon this assumption that A is SPD. If it's non-quadratic, then it can't be written in this simple form, but it may still be an energy which has nice properties. Like, for example, it could be non-quadratic, but it can still be strongly convex. For example, here's an energy which is not quadratic. Not quadratic, which is still strongly convex and Frege differentiable. And if I try to find the minimum of this guy, it's, of course, the minimum is going to be found by solving the Euler equation. What's the Euler equation in this case? Well, it's just going to be x cubed plus beta x equals 0. And what does that look like? That's solving this equation. The only solution for that is x equals 0. So I can find the solution to this problem. So here's an energy which is non-quadratic, but it still satisfies all the properties that I want. If I looked at this same basic example, but in a higher dimensional setting, then I could do this subspace decomposition. And what I would get out of that is something called the nonlinear Gauss-Seidel method. Okay, nonlinear Gauss-Seidel. And basically, I'm optimizing along one-dimensional subspaces each time I update in my Gauss-Seidel method. All right, so I guess I'm trying to say this. So take this energy and boost it up into higher dimensions in a form which looks like this. I guess we could put minus xf, right, if you wanted. Or maybe let's use b, because that's a little more standard. There we go. And if I solve this problem, then I'm going to, in one dimensions, this is still doable. But what I want to think about doing is pushing this to a higher space dimensional analog. Okay, something in Rn, for example. And I'll leave it to you to do that generalization. Now I'm going to apply this decomposition, and the thing I get out in the end is something called a nonlinear Gauss-Seidel method. We're going to keep harping on nonlinear Gauss-Seidel again and again because it's very important in this successive subspace optimization approach and setting. Okay, so Gauss-Seidel, successive subspace optimization method, highly related. All right, this is as far as we got last time, so we're finally caught up to where we were last time. The basic idea of showing convergence is to try to show that we've got an energy contraction which looks like this. And where rho is independent of k and is a number which is between 0 and 1. Okay. The smaller that rho is, the faster we have convergence, okay? And what we want to find is a rho which is kind of independent. So what was wrong with the gradient descent method that we had previously? Well, the rho deteriorated as the nonlinear condition number got larger. And I think, if I'm not mistaken, the gradient descent method had that optimal convergence rate. Well, the problem is L over mu it generally gets large as the size of the problem gets large. So that's not necessarily good. And we want to try to find something which avoids that. And this SSO method is going to avoid that. So that's the good news. Rho is going to be found to be independent of the nonlinear condition number. But the analysis is a little bit more tricky and kind of more complicated. Now, why is this statement here? Why does this statement turn out to be a convergence statement? Well, it has to do with this thing we call the quadratic energy trap. We can convert this contraction into a contraction of norms. So that's the important part. But now think about what's going on here. U is the minimum, okay, the global minimum of E, and UK and UK plus 1 are just are the elements of the output of my SSO algorithm. These guys are not the minimum, right? But they're getting close to the minimum. These numbers should be shrinking. This number should be bigger than that number, and this number should be bigger than that number. Okay, so first of all, these two numbers are always going to be, in general, positive. So that's kind of a sanity check to see that this all makes sense. This minus that should be a positive number. This should be bigger than that. Okay, same with this. But now I'm contracting those positive numbers. Okay, so they're getting smaller, 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 smaller. And the only place that they have to go is down to 0, it turns out. And we're gonna show all that in the next couple of slides. But this is the goal. Try to establish a statement which looks like that. All right, so we need to, there are plenty of results like this out there in the universe. So this is a monotone convergence result, and it turns out to be the one which is perfectly suited for our needs, as we'll find out shortly. So suppose that D is a sequence of positive numbers. It could be, I guess, equal to 0, but generally speaking, they're positive. So these numbers are, okay, non-negative. And suppose that there's some constant C independent of K, such that for every K greater than or equal to 0, dk plus 1 is less than or equal to C times the difference dk minus dk plus 1. All right, then for k greater than or equal to 0, dk plus 1 is less than rho times dk, where rho is equal to a number that is clearly going to be between 0 and 1. So C is a constant, so think about C as being something like 3, and then this rho would, in that case, be 3 over 4. So there's a number between 0 and 1. And it doesn't matter what C is, any number of this type is going to satisfy that. So if C is equal to 2, then this is 2 over 3, etc. This number is always between 0 and 1. And so if that happens, then we can show that that sequence has to converge monotonically and also linearly, or at least linearly, and it has to converge to 0. There's no other place that it can go. Okay, it's got to be monotonically decreasing, and it's got to be going to 0. Let's prove this. It's such an important little lemma. We use it all the time, so let's get a proof for this. So since C is greater than 0, inequality 7 follows from a simple algebraic manipulation from this assumption. So I'm going to leave it to you to do that. It's not very difficult. It's just a couple of lines to show that this implies this, where rho is equal to that that fraction. All right, so 7 on its own then implies, so we get directly from the assumption to 7. 7 implies that dk is monotonically decreasing. So therefore, the monotone convergence theorem kicks in, right? So if a sequence is non-negative, then it's the monotone convergence theorem says that there's some gamma greater than or equal to 0 to which that sequence must converge. That's monotone convergence theorem from analysis, 447. That is math 447 here at the University of Tennessee, or your advanced calculus, wherever you took it, or introductory real analysis course. So monotone convergence theorem says that, but now let's prove that the only possibility is that that constant has to be equal to 0. So let's suppose to start with that that constant is not 0, but is greater than 0. So the monotone convergence theorem says that, of course, this should be, I think that should be, it's a typo there. I think that should be k plus 1, right? Oh, no, it is not. It's not a typo. I was just seeing the same k, but they're actually two different k's. So monotone convergence theorem says that there is a k such that if k is bigger than capital K, so that's capital K, that's little k, then of course, since it's monotone decreasing, since little k is bigger than capital K, this number is going to be less than that number, right? But I can always choose k big enough so that, of course, this is the lower bound of the sequence. This is the thing to which is converging to. And now, by a property of monotone convergence, I can say, well, since it's converging to gamma, this is like gamma plus epsilon. So because I'm going to be within epsilon of gamma for any epsilon, I can choose my epsilon however I want. I'm going to choose epsilon to be like that. Okay. And you'll see that that choice of epsilon is very important for us. Now, I should say that this fact alone, that may not, let's see, is that enough? Basically, I'm using monotone convergence, and I'm going to eventually use either this one or that one. Let's see, which one did I use? So we'll figure it out. So I'm using monotone convergence. Knowing that it's monotone isn't enough to say that that gamma is equal to 0. So that's what we're aiming at. I'm picking this to be epsilon. Okay. So now, right. Okay. So I am going back to that. Okay. So now, since for k bigger than capital K, we always know that this is true, right? That's just by definition. That, or not by definition, that's the thing that follows from the assumption. That's 7. So we have that. Okay, now I'm going to put in the fact that this dk is always less than that, right? So I'm going to replace dk with this larger number. So I get this, okay, multiplying that out. When you multiply that out, you can collect terms, and you find that that's just going to be 1/2 rho plus 1 times gamma. Well, what do we know about 1/2 rho plus 1? So that is a number which is strictly less than 1. That's a number which is strictly less than 1. Remember, rho is less than 1, so rho plus 1 is less than 2, and 2 divided by 2 is strictly less than 1. So this number is strictly less than 1 as claimed. That's strictly less than gamma. So now I've arrived at a contradiction. I've said, if this is true, then the next one is actually going to be less than gamma. Well, what then could I have contradicted? Gamma is my limit point. The only thing that can be contradicted is my assumption that gamma has to be positive. So it must be that gamma is equal to 0. So that's the proof. All right, now we have that little lemma. Put that in your pocket for just a moment. If I know this, then I immediately know 7. Plus, I know that this 7 implies that I have monotonic linear convergence to 0 for that sequence. So I'm going to try to show, so in this context, I'm going to try to show that the d, k plus 1, is less than rho times dk. And that's going to be, those are going to be my d and dk plus 1 and dk. So the idea is, can I show that my dk plus 1 and dk satisfy this? So that's going to be the trick. To do this, I need two more assumptions. okay, for my SSO method. And in fact, these types of assumptions are going to be needed for any method that I construct. Basically, if I have a subspace decomposition and I can show that my method satisfies something like this and something like this, then I'm gonna be able to use that last lemma and conclude convergence. Okay, so what are these called? Okay, what and how are they useful? 8 is called a lower bound on corrections. There exists a CL greater than 0 such that for all k greater than 0, EUK minus EUK plus 1 is greater than all the sum of all these corrections. CL sum I equals 1 to n. So these are my corrections here. And really, I'm by sum of corrections, I mean the sum of the norms squared of the corrections, okay? EIK in norm squared. Now, what this is going to say is that there are a couple of things that this is going to say. So first of all, this has to be positive, right? So, and this kind of makes sense in the context text of my SSO method. That should say that this is positive. Well, how is this possible? Well, this is only possible if this number is greater than that number. Okay, so this energy is greater than this energy. That means as I take steps in my SSO algorithm, this number has to be smaller than this. Or in other words, I have to be going downhill in the energy, or I have to be going in the downhill direction in my algorithm. And downhill just means that when I look at where I'm going on this topographical map, I'm heading in this general direction, right? I'm heading in that general direction. Now, I might not get there in the fastest possible way, and I might zigzag or take some circuitous direction, but I'm basically going in the downhill direction. I start up here, uphill, UK plus 1, and eventually I get down here to UK. Okay, and then hopefully I keep going, and eventually I make my way down to the minimum, which is U. Well, that makes sense in the context of my subspace correction method. My successive subspace optimization method is because when I take those energy sections, I'm always going downhill, because that was the picture that we drew earlier. Basically, you're always going downhill. We started out here, and then we went here, and then we went here, and hopefully we're going to wind around, but we're always going downhill. That makes sense from the description of the method to begin with, right? EUK minus EUK plus 1. This has to be positive, and it has to be greater than the sum of corrections, or the sum of the norms of these corrections, with this constant CL. We also are going to need an upper bound on corrections. Now, upper bound on corrections is going to be a way of controlling how fast we're actually getting to the true solution. So this number minus this number, already we know that that's positive. How do we know that? Well, let's look at this number first. U is the minimum, so it's the smallest possible value. And UK plus 1 is not the minimum, so that's at a larger, higher energy value. So this minus that has to be positive. But it can't be too large. It has to be less than a constant times the sum from I equals 1 to n of the sum of EIK norm squared. So these are the same corrections that we're generating from the SSO method. Okay, SSO method generates, did we call them corrections? Yeah, subspace corrections. That's those elements of the Hilbert space there. Okay, these are each, because of this minimization problem, elements of the subspace VI. Okay. So now notice that these are two different things. EUK minus EUK plus 1 and EUK plus 1 minus EU. Okay, both of these guys are positive quantities, but they're different things, different objects. They both relate back to the original energy. Now, if these two assumptions are true, then all we have to do is turn the key, apply the last lemma, and we're going to have the convergence that we want, which is stated in equation 6. So let's prove that that's true. Suppose that U is obtained, or the UKs are obtained by the SSO method, and assume that the lower and the upper bound on corrections hold. So that's the lower bound on corrections. This is the upper bound on corrections. So by the way, I'm not saying that these things make sense yet, and where they're coming from is maybe a puzzle to you at the moment. Not saying what they mean or where they're coming from, simply saying we can assume that they happen. If those things happen, then the sequence of energies satisfies 6. So 6 says that. And if this holds, then this guy is actually going to have to converge to this, because we know that the difference is converging to 0, so that has to converge to that. That, by the way, is also going to guarantee that we have norm convergence. Okay, so that satisfies 6. Consequently, the sequences converge monotonically and at least linear to EU. And these guys, the sequence, the original sequence that we had, not just the sequence of energies, also converge at least linearly to U. That's a powerful statement. All right, so how are we going to do this? Well, the key is to get the right definition of the D sub k sequence. And the right definition is going to be dk is equal to E of UK minus E of U. So the first thing we want to say is that this guy should be dk should be a positive or a sequence of non-negative numbers, right? So here's E of UK up here. Here's E of U, right? This is the function that we want to minimize. So that has to be dk, that difference. Now, somehow we move, and so here's UK, E of UK, UK. Somehow we move to UK plus 1 through our algorithm. And that's got to bring us down the energy curve. It's got to bring us closer. Well, for now, all we know is that it has to bring us down. Okay, so we get to E UK plus 1. So this value here is dk plus 1. And the difference of these two values is this guy here. Okay, the difference of this value and that value. Okay, that's what we call dk minus dk plus 1. This is a positive number. dk is bigger than dk plus 1, so dk minus dk plus 1 is positive. That's the sequence of dk's that we're going to use in our proof. So it's defined right there. So that's our figure. That's the figure to guide us, hopefully. Now let's take the difference of these two. What's dk minus dk plus 1? Well, that's that energy difference, EUK minus EUK plus 1. How do you see that? Well, dk is EUK minus EU. So if we take dk minus dk plus 1, that's equal to E of UK minus E of U minus EUK plus 1 minus E of U, right? And then you see right away EU cancels, and you just get EUK minus EUK plus 1. And of course, you could have seen that from here. Okay, that's just the difference of those two energy values. But there you go in any case. All right, so what is that value? That's the energy decrease associated to the k plus first iteration. All right, now by assumption 9, that's the upper bound on corrections. Assumption 9 directly gives us this information here. dk plus 1, which is going to be that guy, the difference between EU k plus 1, EU. That's that. That gives us an upper bound on corrections. That's 9 right there. And now we also have a lower bound on corrections, right? And the lower bound on corrections says this here is going to be less than that, okay, because that was the assumption, okay, but with a factor of CL in there. Okay, so what do I mean by that? So I need to have this. What I'm going to do is I'm going to take this CL and move it over to the other side, I guess. Okay. So multiply or divide both sides by CL. Well, that's going to allow me to replace this instant here with this constant over CL. All right. And that's how I get to this. Okay. You can work it out on the side. But in any case, I get from dk plus 1 to the difference of dk's with a constant. Okay. Now, this constant, I don't care what its size is. I just need to know that it's a constant. Okay. But lemma set the previous lemma tells me right away that if I don't care about what that constant is and I simply have that, tells me right away that 7 has to hold right here. Okay. From that, I get 7 with that row. Okay. Whatever constant appears in front of there, my constant of decrease is going to be that constant over 1 plus c. Okay. Whatever that constant is, constant of decrease. Okay. C over 1 plus c. That's my row. But now just multiply the top and the bottom by CL, and you immediately get this simpler version of that constant. All right. So that guarantees that the linear convergence of this sequence to EU because of what we had in 6. Okay. This must converge to EU. That's the only possibility. And the rate row is guaranteed by the last lemma. And it turns out we won't see this right away, but this row can be a lot smaller than it is for the gradient descent method. And that is the great utility of this method. That this row, which we're going to see in the next chapter, is so much smaller than it could be with the general vanilla gradient descent method. Now, how do we get from that converging to that to actually UK converging in norm to U? Well, to do that, all we have to do is use the quadratic energy trap. Okay, so remember, we know that as long as W is, so W and U have to be in this ball. Of course, U is in the ball, no problem. So W can't be too large or else this constant is going to get larger and larger. But the ball that I can use is the so-called energy ball. Okay, I know that I'm always going to stay in the energy, or the energy is always going to be less than a certain value, basically dictated by E0. Because I'm always going downhill, I know that my energies of the EUKs all have to be less than E of U0. So that ball, or that sublevel curve, sublevel set, dictates where I'm living. And so that dictates for me what is the value of that L. Well, I'm going to apply that quadratic energy trap, which has that value of L associated with with this energy dictated above, okay, where W is equal to UK. All right, once I do that, then I can immediately conclude that we have this type of inequality. All right, so if this is going to 0, which it is, and it's going to 0 linearly, that is going to suggest, or actually imply rigorously, that this norm, or norm squared, is going to 0 with a certain rate, a linear rate. But if the norm squared is going to 0 at that rate, then the norm actually has to be going to 0 at a linear rate as well. And so I'll leave the details to you to show that, but that's the idea of the last part. How I get from the fact that E of UK converges to E of U linearly implies that UK converges to U in norm, okay? And if I want to say in norm, then I put the little Hilbert space symbol above. All right, so now the next steps become clear. I want to verify that the lower and upper bounds on corrections 8 and 9 hold. If I can do that, then I can apply the lemma, turn the key, and I have the convergence of my SSO method. All right, so the next step for subspace optimization methods, as I said, are proving that the upper and lower bounds on corrections hold, and then we can apply the last lemma, and then we'll have convergence. So the next steps are clear. We want to show that 8 and 9 hold. So it turns out the lower bound on corrections is quite easy to do and just follows straightforwardly from our assumptions. The upper bound is a little bit harder, but now when I do the upper bound, you're going to get to see why I've made these assumptions about the strength and Cauchy-Schwarz inequality, et cetera, et cetera. And that, well, strength and Cauchy-Schwarz and also the stable subspace decompositions, where those will be important. Now, the lower bounds don't really care what the subspace decompositions look like. All I need to assume is that E satisfies E0 and that I have some subspace decomposition in place. Then if I compute my subspace, or if I compute my sequence via the SSO method, then condition 8, that is the lower bound, holds, and the lower bound constant is going to be mu over 2. All right, so owing to the previous lemma, then every energy section that we in the SSO method that we need to optimize over is Fauché differentiable. And furthermore, it inherits a lot of the other structure of E, like, for example, it inherits the quadratic energy trap, et cetera, et cetera. Remember, we pointed out that it also satisfies this concept of the fundamental orthogonality. So we argued previously that this guy has to be equal to 0 in VI prime, okay? Or in other words, this is equal to 0 for all V or all W in VI. And that simply means or implies that that derivative is equal to 0. Okay, so that's the result of doing each one of my my optimizations along these energy sections. If I do that, then I'm going to have this fundamental orthogonality. All right, now we're going to define, or actually we're just going to realize that EI can be realized as VIK minus VI minus 1K. So if you want, just move this guy back over and you'll see that when I add this correction onto that, I get the updated value of my iteration. Now I have a result from the last chapter which says that I have this quadratic energy trap, the lower bound. And so that is just this statement. Another way of looking at that statement there is that is just a statement of the definition of strong convexity. Okay, so strong convexity implies that I have that. Well, now that's going to be a key component in showing that I have this lower bound that I need to show. Okay, so I need to show that this guy is bounded below by stuff that which looks like that. Well, what I'm going to do is I'm going to realize that this can be written as a sum of different things. For example, I can say that EUK, that is equal to, well, so let's see, minus, let's write it like this. Um, how do I want to do this? Well, first of all, yeah, I want to first of all recognize that UK, that's just going to be equal to V0K, right? That's how I initialize thing. And then this guy here, UK plus 1, so now I see. So this is equal to VNK, right? So I can rewrite that using these two V's, but then I can just put in between them energies of the intermediate values and then realize that that's some telescopes. So in other words, I can rewrite that simple difference as the sum of these differences, okay, using these two very simple facts. And I'm going to put intermediate energies in there in between. Next, I'm going to realize that I can replace that by that, okay, just from the definition or realizing that each section is strongly convex. Okay, each energy section is strongly convex. And so I'm able to replace each one of these by these differences here. So I immediately get it. You see, mu over 2, sum I equals 1 to n of the corrections in norm squared. That's exactly the lower bound. I'm done. All I have to do then is identify CL is equal to mu over 2, and I'm done. The lower bound is very easy, simple. So we're done with that. So that gives us 8. Now, um, the little theorem that we used, or the result from the last section that we made use of, is the fact that when I have these energy sections, each one of them are nice. They all satisfy the quadratic energy trap, blah, blah, blah. The thing that I really needed to use here is the lower bound portion, okay? Just the lower bound portion. Okay, so how do I get the upper bound? The upper bound, I think I can do that in 2 minutes, and so let's get into it. So for this one, we need to assume that E satisfies E0, but we also need to satisfy, we also now need to bring in for the very first time the assumption that the subspace decomposition is stable and the strength in Cauchy-Schwarz inequality holds. And if we can do that, then we can show that the upper bound on corrections holds with an upper bound constant equal to this whole mess. Okay, so it involves the mu, and it involves these two constants. The first one is for this for the stable decomposition. The first one is, or the second one is for the let's see. First one is for the stability, and the second one is for the strength in Cauchy-Schwarz. Okay. Now, from the previous chapter, we had this result. So this is where we're going to start. Okay, start with that result. EUK plus 1 minus EU is less than 1 over 2 mu times the operator norm of the derivative squared, evaluated at UK plus 1. So that's the place where we're going to start. Okay, now we're going to observe that we're minimizing, that when we solve the minimization problem on each subspace, we do so exactly. So therefore, we know that the energy is always decreasing. And this guarantees that if we use this as our as our finite set, that this guy is convex and it's a bounded set. Okay. So we know that all of our points are going to be in this set B. In fact, all of the iterates, individual iterates in between, are all going to be in B. Okay. Moreover, we know that the fundamental orthogonality property holds. Okay, so we're going to take advantage of that. And now we're going to invoke the stable subspace decomposition. Okay, so let W be in V. Invoking that stable subspace decomposition, we could always take or find a decomposition W such that that's going to be I have that decomposition, and I know that that decomposition is going to be stable. Okay, so now I'm going to start with this guy here, and I'm going to estimate, or I'm going to put in my various properties. Okay, so the first thing, this is due to breaking this up into my subspace decomposition. W equals the sum of WIs. Next, I'm going to put this guy in there. That's equal to 0. That's the fundamental Galerkin orthogonality. Okay, that guy is 0, but it's 0 when I test it against any one of these guys from the space VI. Fundamental Galerkin orthogonality. Next, I'm going to decompose this guy. I'm going to rewrite this, okay, using the fact that that's just that telescopes, and I can rewrite this in terms of the V's. Okay, so I'm going to rewrite, this is already in terms of V's. I'm going to rewrite this in terms of V's as well. Okay, that allows me to write that double sum. All right, now, let's see. So now I use 4. What was 4? Oh, that's just the definition of this guy. That stays the same. Now this sum is exactly of the type that I want to apply my strength and Cauchy-Schwarz inequality to. Okay, strength and Cauchy-Schwarz, which is called condition NS2, says that if I take the absolute value of that, that's less than CS times that times that. Okay, so this looks like the sum of corrections. And this is my sum of my decomposition here. Well, now I can use the fact that my decomposition is stable. So if my decomposition is stable, that's less than the stability constant. I forget whether stability is that one or that one, so forgive me, times W. Okay, so I can use that one first. This is where I've used strength and Cauchy-Schwarz. So I've used both strength and Cauchy-Schwarz. Oh, yeah, so this is strength and Cauchy-Schwarz, and this is stability. And I've used stability, which is that one. All right. So now I have from that result 2 slides ago here, and from this estimate here, using the definition of what this norm is. Okay, that norm is an operator norm, which is given by that. So now that operator norm involves this definition. I just showed on the previous slide that this is less than all this mess. Notice that, therefore, I can divide out that W norm. Okay, and so I'm taking a super over W's, but the W norm gets canceled out, and so that is my upper bound. So this gives me my upper bound on corrections. So I can now identify the CU with that constant right there, and I'm done. So that proves the convergence that I'm looking for. All right, so all I have to do is apply the previous lemma and the fact that I've just shown that I have the upper bound on corrections and the lower bound on corrections, and I immediately get this convergence rate for my energies. Okay, once I know that the energies converge linearly, then I can show that the iterates actually converge linearly, and I'm done. There's nothing more to do. Okay, so that's where we're going to end today. You can turn your cameras back on, and I will take your questions.